Yeah, good morning, everyone. My name is Albert Thomas. I'm a faculty from Indian Institute of Technology, Bombay. This study has several authors, around 7 authors. This is a study that we have conducted based on a collaborative project between IIT Bombay as well as Carleton University as part of a research grant obtained from Department of Science and Technology, India, and IC Impact Canada. So that's why you will see a lot of authors there. The first 3 authors are from IIT Bombay. They are basically our students. And the second and the 4th and 5th authors are from Canada, and 7th, 6th author is myself, and Elie is a faculty from Carleton University. I'll be talking about giving an overview of the project, a little bit of background, what the project is, and basically this study is a part of a project, the main project. I'll explain about that in a bit, which addresses a major component. I'll also talk about the result discussion and a bit of conclusions and future works. So this is a snapshot of the project that we are working on. It is titled For Building Healthy Communities in Canada and India. There are several steps mentioned about it. So it is on net zero energy buildings, to identify strategies for net zero energy buildings. So develop, it's basically a study which has building energy simulation modeling, machine learning, and optimization, and finally coming down to assessing the strategies and roadmap for implementing net zero strategies in India as well as in Canada. So there is this step 4 where we have a requirement of developing machine learning models to guide design and operation of net zero energy buildings in lieu of the traditional energy modeling. That is where this particular paper in this conference is coming from, and we are at this stage for this project right now. A little bit of context of the study. I think some of it has been already covered in terms of the buildings and its energy intensity. One point which I would like to highlight here is the building energy simulation is a common technique which is used across different researchers in different countries. It's a technology which helps us to understand how the building, what is the building energy requirements and so on. But one aspect here is that the energy prediction is computationally intensive. It takes time, takes cost as well. That is one limitation of building energy simulation when you are trying to look at for a lot of buildings and so on. And the accurate building energy forecasting system can save about 30% of the total energy consumption. So it is a tool which can help in this overall perspective. Then machine learning based surrogate models help overcome some of these limitations of BES models. There have been several studies that have been done that uses machine learning based techniques to surrogate this entire process, so that then you can use that for understanding quick design solutions. So when you look at the gap in research, the existing literature on machine learning focus on annual energy prediction, which talks about a particular value for a year based on different input parameters and so on. This is one gap that we are trying to address in the study by using hourly energy prediction, especially targeting building retrofits such as renewables and so on. So that's the major focus point in this particular study. These are some of the literature that has done machine learning based techniques for energy prediction. Basically, there are 4 stages for this study. The stage 1, we have developed a reference building model. Especially when you look at from tropical countries such as India, you don't have much studies that talks about the data availability is a big issue. And there is not any study that has done machine learning based surrogate techniques for different types of building in India. That is one aspect that we have started with. We have developed a validated prototype commercial building model based on some of the data that from one data collected from one other study. And this model is, we developed a model and it has been subjected to several simulations based on different climatic conditions. And as for any other ML study, we have developed a data set generated a data set for 1 year in an hourly precision, and we have selected some of the data for 4 climatic locations. We have these data points. So basically we have the input data points as well as the output is basically the energy consumption. And we have tested 4 machine learning algorithm, because in the several studies have reported several machine learning techniques. So you basically have to understand which one is better in terms of surrogate modeling. And we have used a few evaluation metrics as well. And in the stage 4, so this is pretty much a typical way of doing machine learning surrogating. And after that, we have done a couple of scenarios. I'll talk about that to understand how this machine learning model, or the best performing machine learning model, how that works for the Indian conditions. This has only Indian buildings data, and we are now replicating this for the Canadian side. This is details of the reference model. I'll go a little bit quick here. These are some of the typical details of the building model. And the data generation for machine learning training, as I said, the total simulation data points are 8760, basically the 8760 hours for a particular year. And we have used an 8-hour schedule from 9 a.m. to 5 p.m., which means that we are down with 2000 data points. And out of that, we have selected these input variables, and the output variable is basically the hourly energy consumption. And we have around, done machine learning based model development here. We have used 80-20 training and testing, as we have heard from the previous study as well. Which is basically the standard method that you use. And we have developed 4 machine learning algorithms: multiple linear regression, polynomial regression, random forest regression, and artificial neural network. This is some explanation of the methods, a little bit more details into how we have done it. We have basically used the Python-based collab system. So coming to the results, so once I'll talk about that, and once we have identified the best machine learning algorithm, which is the RFR, and we have done 2 scenarios to check the overall prediction capability of the RFR model, which is basically the scenario 1. And we have used all the data, and we have done it for 4 climatic locations, which is Ahmedabad, Kolkata, Bengaluru, and Lucknow, which are basically the ASHRAE-based weather systems in India. And in scenario 2, we have used the data from 3 cities and to see whether that machine learning model is helping us to predict the energy consumption of the 4th city. That's what the scenario 2 that we have done. And it is, with sufficient accuracy, it is helping us to predict the 4th city. So that is one of the takeaways from the study that has come up. The typical model performance and evaluation metrics that we have used with the ASHRAE guidelines, such as the coefficient of determination, mean square error, root mean square error, mean bias error, coefficient of variations, and so on. Coming to the model performance and evaluation metrics, for what you are seeing here is for 4 locations: Lucknow, Ahmedabad, Kolkata, and Bengaluru, which are the climatic locations. And based on these, the evaluation metrics that we have established, we found out that RFR is the best model, best performing model in terms of all the metrics. And we have chosen that. And for a particular city, Lucknow, we have plotted this to see. What you are seeing here is basically the red, which is the RFR, which is showing a nice plot here in terms of the actual as well as predicted value. Now we have chosen this RFR model as for conducting the 2 scenarios that I've talked about. In scenario 1, we checked the overall prediction capability of the RFR model. This is basically, we have taken all the data from all the locations and tried to predict using 80-20 rule. In scenario 2, we have taken from 3 locations, and for the 4th location, we have tried to predict. So there is some decrease in the accuracy, but still it is coming within the range. So the application of this technique is that you can predict for one more location or a few more locations based on the data that we have. Coming to conclusions, we have used ensemble-based models such as RFR model. This is suitable for energy prediction in hourly resolution, and we have tested 2 scenarios that I talked about. Future works, we can use some other methods as well. Literature has also been using that. That is one of the things that we are doing. And as I talked about in that big project, we are planning to do it for the Canada as well, and further optimization and so on. As a summary, the study has used an archetype commercial building. It can be extended to the other building typologies and weather locations as well. And our sincere acknowledgements to the funding body as well as to all the authors. Thank you.
Thank you very much for the very interesting